Alright guys, so in this section we're going to be talking about the right triangle trigonometry, and first of all we're going to see what a right triangle is. So a right triangle, it's just a triangle that has a 90-degree angle. This is how we represent a 90-degree angle. We call this a right triangle. Now the other two angles on the triangle, or in this case of the right triangle, are going to be acute. And an acute angle is just an angle that is less than 90 degrees. So we're going to take one of these acute angles and say we're going to call it theta. We call the side that is opposite to the angle of interest, in this case theta, will be called the opposite side. Now the side right next to our angle theta here would be called the adjacent side, and our third side here opposite to the 90-degree angle will be called the hypotenuse. So here we have it, our right triangle with our angle theta and the corresponding sides with respect of this theta. So if we had the other angle here, if we were looking at the other acute angle, then these two would switch, right? This will no longer be opposite, this one will be opposite, and the adjacent will be opposite, and vice versa. So there are the names of the 6 trigonometric functions. We're going to use abbreviations to, so that we don't have to write the whole word. So the 6 trigonometric functions mentioned here are going to, of our angle theta, are going to be defined as follows. We have sine, the first one would be sine of theta is equal to opposite, and I'm abbreviating a little bit there with the words, over hypotenuse. Cosine is going to be adjacent over hypotenuse. And then we have tangent of theta. It's going to be opposite over hypotenuse. Now the other three, I'm going to put them here on this side that you see. I'm purposely going to pair them like this because you're going to see that the other three are going to be reciprocal of the first three. I'll start with cosecant theta, and that's the abbreviation for it, is hypotenuse over opposite. Then we have secant of theta is hypotenuse over adjacent. And then finally, cotangent of theta would be adjacent over opposite. So notice how those last three are really just the first three flipped. So, but here are the definitions of the 6 trigonometric functions of this angle theta based on this triangle here, the right triangle. Later on, we're going to graph all these functions. So keep in mind that these are functions, so they need an argument, right? So they need this theta here. It doesn't make sense to say sine, just sine of nothing. We have to have an angle, a number as an argument here for each of these functions. Now, if this is your first time seeing these ratios, the definition of the trig functions in this way, there's an easy pretty straightforward common mnemonic that is used to help you remember this trigonometric functions. So we have, I'm going to write it over here, SOHCAHTOA. It's a little mnemonic that is used, or acronym if you want to say it that way. So you can see here, this is sine is opposite over hypotenuse, cosine adjacent over hypotenuse, and tangent is opposite over adjacent. This acronym is just good for the first three, but remember what I said here. If you remember this first three, right, you can deduce the other three just by taking the reciprocal of the first three. Just remember which one goes with which, right? Because at first it's easy to getting mixed up. Okay, so let's do a quick example here. Let's say we have this triangle here, right triangle. We're gonna label our theta, our angle theta. This is side 3, this is side 4. And the question is find all 6 trigonometric functions. Okay, so notice how this problem, you're given 2 sides out of the 3. We need all 3 to be able to, we need this hypotenuse here to be able to find all 6 trig functions. So this would be a good point to mention a very common theorem here that puts all the 3 sides together, and that is the famous Pythagorean theorem, which says our hypotenuse here, square, is equal to the opposite side square plus the adjacent side square. Right? Some people know, remember or know it as a squared plus b squared is equal to c squared, but we'll have to label which one is c and a and b. So here, going back to our original triangle here, you know, with respect to this theta, we have an opposite side, an adjacent side, and a hypotenuse. So I'm using those that notation here, but that's a Pythagorean theorem. So we're going to use this first to be able to find the hypotenuse, and then we'll have all 3 sides and be able to find the trig functions here that we're looking for. So let me set it up. Okay, so there we have it. It's just a pretty straightforward calculation here. So we have hypotenuse squared is equal to the 4 squared plus 3 squared, and then we add that up, take the square root on both sides to get just the hypotenuse, be square root of 25, which is gives us a nice 5 there. So this hypotenuse is 5 there. So now we're able to find the trig functions of theta here. Sine of theta would be, remember, go back to our definitions here. So katoa, sine is opposite over hypotenuse, opposite of theta is 4 over hypotenuse 5, right? Cosine of theta would be adjacent over hypotenuse, tangent of theta, opposite over adjacent, and then the other 3, remember, if you remember, those first 3 are easy to calculate. Just remember, cosecant is reciprocal of sine, so that's 5 over 4, hypotenuse over opposite, and we have secant is the reciprocal of cosine, so it'd be 5 over 3, and then cotangent would be 3 over 4. And there we have it, right? So those are the 6, and you know, we leave them as fractions, that'll be fine, because they're ratios. We can put those fractions in the calculator and get a decimal, it's the same thing, but we're going to keep them as fractions for right now. So I want to discuss a couple other examples of 2 special right triangles, and we're going to be seeing a lot moving forward. So the first one is the 45-45, 90 right triangle. So we're going to write them in here, and this one of the acute angles is 45, then the other one has to be 45. I didn't mention this earlier, guys, but hopefully everybody knows that the sum of the 3 angles on any triangle, doesn't have to be a right triangle, but any triangle, it's 180 degrees. So we're only dealing with right triangles right now, which means one of the angles is 90, the other one is 45 in this case, so the third one here will have to be 45. So that's where we get the 45-45 90 right triangle. Now if we let this side be 1, this opposite side to 45 1, then this will have to also be 1, right? Because this is also 45. So this is what we call in geometry an isosceles triangle, right? So same angles yield same to the same sides. And then if you don't know what the hypotenuse is, we can always do Pythagorean theorem to figure that out, right? We can do it here on the side. So this right here happens to be square root of 2. Now, remember, similar triangles have the same angles, just different sides. So you may have a 45-45-90 triangle that is larger, but because they have the same angles, you're going to maintain this proportion here. So in other words, if you have if this side is 5, then this will have to if this side is 5, this side would have to be 5, and that would be 5 square root of 2. So in other words, the proportion is going to remain here. So if we let this 1k, 1k, and k, no matter what k is here just some arbitrary number, then that proportion would remain there to guarantee that we still have a 45. Okay, so now notice here the k is irrelevant when finding the trigonometric functions. Let's go ahead and find the 6 trigonometric functions of this 45 triangle. So let me do one here on the side. So if we do sine of 45 degrees, by definition sine is opposite, so opposite over hypotenuse. So we're going to have 1k over the square root of k. Now notice how the k's go away. So this ends up being 1 square root of 2. 1 over the square root of 2. Okay, so that's why I said the k's will cancel out, because all the trig functions are just ratios. That's just indicating proportions here of this triangle. So let me go ahead and write all the trig functions of this angle 45. Okay, so here we have it. Now, one thing that I missed to do here is once we got here the sine of 45, we got sine 45 is 1 square root of 2. Now, remember in math, we don't like to have a radical on the bottom, so we typically just rationalize this part by multiplying both sides, or top and bottom, by square root of 2, and this gives me the square root of 2 over 2. So that's what I have right here. Cosine happens to be the same because it's adjacent, but adjacent is the same thing as opposite here, so it's still 1 over square root of 2, which rationalized will turn into square root of 2 over 2. Tangent is opposite over adjacent, that's 1 over 1, so that's just 1, and then the other ones, of course, are the reciprocal of the first 3. Okay, so in the same way, we have the 30, 60, 90 degree right triangle, and this comes from, basically the idea comes from, if I draw an equilateral triangle, which is, pretend this whole triangle, the green part and the black one too, all together, this big one here is an equilateral triangle, which means it's a triangle that has all 3 sides are the same. So if all 3 sides are the same, all 3 angles are the same. Remember we said the sum of the 3 angles is 180 on any triangle. So then each one has to be 60, right? Now, if I draw up a perpendicular here on one of the sides, it doesn't matter. I'm just picking the one on top here just to make it easy to see. If I draw up a perpendicular, because all of these sides are the same, this perpendicular is actually bisecting this angle here, and it's also cutting this side where it lands here in half. So for the sake of argument, if just to make put nice numbers in here to the sides, if I let each side of the equilateral triangle be 2, that's 2, this is 2, this bottom one will have to be 2, but because this height cut it right in half, then this will have to be 1, and that will have to be 1. Now look at just the triangle, the right triangle in black. I mean, they're both the same, but just look at this one here where the 60 is. And then you see the hypotenuse here is 2. The the adjacent side of 60 is 1. So if we wanted to find this opposite side, then we just do Pythagorean here on the side, right? Pythagorean theorem, and then we get, 2 squared is equal to 1 squared plus the opposite side square. Okay, well that's 4 equal to 1 plus opposite square. Subtract the 1 from the 4, you get 3 equal to opposite square. And then finally, opposite is just square root of 3. So this part right here is square root of 3. Okay, and then I'm only looking at the right triangle now, and we can now figure out the trig functions of 60. And there you have them. Now we can use the same triangle here to come up with the trig functions of the 30, Because if we use the same triangle right here, this angle right here is 30 degrees. Now remember, now the opposite and adjacent change. If you're taking this 30 to be your angle here, we're going to have, now sine of 30 degrees is going to be opposite of 30 is 1, not square root of 3. 1 over the hypotenuse is 1/2. Cosine of 30 would be square root of 3 over 2. Tangent of 30. Rationalized, it would be square root of 3 over 3. We have cosecant of 30. It's 2. Secant of 30 is 2 square root of 3 over 2. Again, rational over 3 and rationalize, already rationalized, and cotangent of 30 would be square root of 3. Now, hopefully you get to see some pattern emerging here on the trig functions between 60 and 30, of 60 and 30 here. Now notice how the sine of 60 is actually the same thing as cosine of 30. And cosine of 60 is the same thing as sine of 30. So from here, from this example, we can sort of derive some identities here. They're called the cofunction identities. Okay, so notice how we have 3 of the trig functions that we have start with the prefix co. So that's going to give you the indication of which one is a cofunction of which. So notice how we have sine and then cosine, right? It has the same word in it with the prefix co. Tangent, cotangent, and we have secant and cosecant. So that's how you know which one's cofunction of which. But basically, from this example, we can deduce, we can have the cofunction identities. And we're going to talk about these a little bit later too, but this will be a good place to introduce them. So notice how this theta is just some arbitrary angle. Of course, has to be a more than 0, less than 90 degrees. So an acute angle, in other words. And this is going to be its complement right here, right? Because if you subtract theta from 90, you get the complement of it. Okay, and then we can do the other two as well this way. So this cofunction identity is coming handy when you want to accelerate the process a little bit, or you already know the trig function of an angle, an acute angle, then you automatically know the cofunction of its complement. So that you don't have to actually compute or do all the ratios, you just automatically know it because these identities are true. Okay, so there are other identities that emerge from our basic definition here. So for instance, reciprocal identities. Okay, so there we have them. These are pretty straightforward, guys. I mean, from the beginning of our definition, we said, the sign, we put him, wrote them in this way so that you will see sine is reciprocal of cosecant, because their ratios just are reciprocal of each other. So that's where these reciprocals come from. Sine is going to be 1 over cosecant, and vice versa. Cosecant is 1 over sine, right? And then we have cosine is 1 over secant, because from the definition, their ratios are just reciprocal of each other. I mean, these are easy to prove just using the plain definition. Now, one thing is that that I want you to make sure is that not to confuse these two, cofunctions and reciprocal identities, because that's a typical mistake here, where if we confuse reciprocal with cofunction, and sometimes we mistakenly think, oh, okay, sine is reciprocal of cosine. No, sine is reciprocal cosecant. Sine is cofunction with cosine. Okay, so that's different. And that yields different identities here. So just make sure you understand what the word reciprocal means, right? If you have a fraction, it's just really you're flipping that fraction, right, or that number. So those are the identities. The other identities that we're gonna get are going to be the quotient identities. Okay, and these are pretty straightforward, guys. There's only two here. We have the tangent of theta is equal to sine theta over cosine. So tangent is sine over cosine. And guess what? From this reciprocals here, you know, tangent is reciprocal cotangent and vice versa. So if tangent is sine over cosine, cotangent is going to be that flipped, cosine over sine. There it is. So we have the quotient identities. And then we have one more set of identities for this part. And those are very important. They're going to be called the Pythagorean identities. Now, the Pythagorean identities get their name from the fact that when you prove them, you derive them, you use the definition of our trig functions, but you're going to have to use the Pythagorean theorem at some point to be able to prove that the identities are true. So, but I'm just going to put the three variations that of the Pythagorean identities that we have here. So all right, so here they are, guys. All these three are called Pythagorean identities because, again, they are derived from the Pythagorean theorem and the basic definitions of the trig functions. But all of these could easily be proven with that basic definition. So I'll just prove one in here. And you can do the other ones as exercise. But they're pretty straightforward. Now remember, the only thing we know right now is the definitions of each of the trig functions here. So let's say if I wanted to prove this one here, right? And we're actually going to see more identities later, but these are the basic ones, the ones that we're going to use all the time. So the sooner you get used to them, the better. So here, if I wanted to prove or verify that this is actually true, I'm going to take one side of the identity and try to conclude, arrive to the other side without manipulating anything on the other side. So I'm going to write here again, sine, and again, I'm just proving one. You can see you can do the same thing, same idea for the other ones. And just kind of deriving that way. It'd be a good exercise for you. So we have cosine square of theta. All right, so we want to prove that this is actually equal to 1, right? How is that sine squared? And this is for any theta, any angle theta, right? The angle is not depending on the angle, it's the functions themselves. So remember, let's apply our definition here. Sine is opposite over hypotenuse. And then, of course, we're going to square that. And then we have cosine is adjacent over hypotenuse. Square that. Okay. From there, we have a fraction square, so that, we can distribute that square to the top and bottom. So we have opposite square over hypotenuse square. Right? This is purely algebraic. Adjacent square over hypotenuse square. Now, notice how the denominator, we have a sum of two fractions. The denominator on here on the bottom here is it's just hypotenuse square. So you know that when you are adding two fractions that have the same denominator, you just add the top, right? So this is opposite square plus not hypotenuse plus adjacent square. Okay, now here's where I still don't see the 1, so here's where you're going to apply the Pythagorean theorem, and this is where it gets its name, right? Remember what we said up here, what the Pythagorean theorem was? What is the Pythagorean theorem? Right here. Hypotenuse square is equal to opposite square plus adjacent square. So if we happen to have this on the numerator of our proof here, so if we just replace this with hypotenuse squared, because we already know that to be true from the Pythagorean theorem, we have that that whole thing can be replaced by hypotenuse squared. I already have hypotenuse squared on the bottom, and voila, we have the same thing. They cancel each other out, so then you end up with the one that is on the other side. So 1 is equal to 1 from our identity there. So we're going to be doing a lot of verifying of identities later on in the next chapter, but there's just a little preview of the process that needs to be done. But again, all of these proofs are pretty straightforward. You can derive and deduce all of these just from our basic definition here from the beginning, because that's all the ones we have. Again, the only ones that you had to use a little bit more with the Pythagorean theorem would be those 3 here, but the other ones are just plain definition. Okay, now that we've defined our trig functions, we've come up with some identities that we'll be using throughout here the subject, the course. We should be able to do some basic applications using our trig functions here. I want to do just one quick example just to show you how these trig functions can be applied at this point. Okay, so let's see this application here. Let's say we have a ramp here. We want to build a ramp, right? And let's say the height here is 3.5 feet. Okay, and let's say we're given this angle here as well. Let's say it's 11.5 degrees, right? And we want to find this x and this y here, where x is the length of the ramp and y is the horizontal length, right? From the tip of the ramp all the way to the base there. So this is a very practical problem, especially like if you're doing something like this yourself and you want to build a ramp. So here we need to figure out 2 things. There are 2 questions here. Now notice how we're giving an angle and we're giving one side. If you look at the right triangle here, you're giving one side, 3.5 feet. Now, if we had x or y, in other words, if we had another side, a second side of this right triangle, then we would be done, right? We wouldn't even need this angle here, because we know we can use Pythagorean theorem. Remember, if we have a right triangle and we have 2 sides, I can always find the third side with Pythagorean theorem. But the problem is that I don't have 2 sides, I only have one, and I'm asked to find the other 2. So here's where the trig comes in, and then of course you have to have this angle here. So the idea is going to be, okay, well, think about your trig functions that we just defined. And let's start with x here. Let's find just that length x first. And we start thinking about, okay, forget about y, because we don't know what y is for right now. We're going to find y in a minute, but like forget about y, just think about x. And then look at everything that you do have. You have the 3.5. And you have the 11.5 degrees, 3.5 feet and the 11.5 degrees. So look at the angle and then start thinking, what trig function puts this opposite side, 3.5, and x together? Which one puts it together? Okay, so then you're going to be like, there's actually going to be, out of the 6, there's going to be 2 that you can use. So which one uses opposite and a hypotenuse? So if you remember your trig functions here, you're going to sine of 11.5 degrees is going to be opposite, which is 3.5 over hypotenuse. Now notice here how we're only finding x, and we can solve for x here by just cross multiplying here. And you're going to get, I'm going to do it every step. Want to make sure you do get, if you put the x on the other side, 3.5, then you can move the sign, divide everything by sine of 11.5. So this right here, you can just put it in the calculator and get the answer, right? Now, notice how, this angle 11.5, we just have to put that in the calculator. So we'll do that. Okay, guys, so in a calculator, I want to make sure that for those that are using TI-84 or TI-83, you make sure you're inputting the values correctly, and then there's some things that you have to make sure you have in place before you do the calculation. For instance, remember we talked about previously, we've talked about you've seen radians and degrees. Well, depending on which one you're using, you want to make sure the calculator is in the right mode. Now we're doing degrees in here. Now typically the calculators are set by default to be in radians. If you go to mode here and just scroll down and move over, you gotta click and make sure you change it to degrees so that this will work. Otherwise it's going to assume you're inputting radians, and that's not what we're doing. You're not going to get it right, especially for when you're doing your applications, right? So then once you do that, you clear that out of there, and you're going to just put the whole thing in there. 3.5 divided by sine of, and now this is going to take degrees because we changed the mode, 11.5. Yeah, you don't have to put just 11.5 already knows as degrees, close parenthesis, and then enter, and that should be the answer. So this is our answer here, 17.6 watt. We're in feet, so this is going to be feet. Now in the same way, we can do find the y, right? So for the y, we can do the same idea, or you can also, since you already have x, you can also do Pythagorean theorem and get a good approximation of it. But just so that we can practice this trig functions, we're going to do it with the trig function. So there we have a 17.2 feet. Okay. Now maybe somebody's asking, well, why couldn't you use cosecant instead of sine? Or here cotangent instead of cotangent. We could have used those, but the problem is especially because you're gonna have to use a calculator. If you put the calculator, you have keys for sine, cosine, and tangent, not the other three. So you want to stick with using those three. Now it's not that you can't use the other, but those three would allow you to do it quickly in the calculator. If you use the other three, like cosecant or cotangent, you're going to have to use these reciprocal identities anyways, because you can't, if you're going to put them in the calculator, you're going to have to use these, which is the same thing. It just saves you some time.